Okay, let's see what we're going to do today. Suppose you have a curve in space, just like we have there in that picture. There's a blue curve, okay? Let's put a name for that. Let's just call that R of t. A vector valued function, let's say, okay? All right, now, you would like some way to quantify the direction that the curve is traveling at any point, right? So an example would be like this. You see at these 3 points, there is a vector pointing the direction of travel. Okay? Now, what do you think those vectors are called? Those are called tangent vectors. Okay, because each one of them is tangent to the blue curve at the particular point. When I say the particular point, I mean this first vector is coming from that point. The second one's coming from this point. The third one's coming from this point. The red vectors at those 3 points are tangent to the blue curve. And that's what we mean by they're pointing in the direction that the curve is traveling. Or I should be a little bit more specific. They are pointing in the direction that a point is traveling if the point is following the curve. Okay, so the curve itself is not moving, but if a point is traveling along the curve, then the point is moving, and at any particular moment you might like to know which direction the point is going, and that's what we use the tangent vectors for. Okay, now in order to keep things consistent, we would like all of our tangent vectors to maintain the same length. Okay, in other words, we would like the tangent vector to always be the same length. Well, okay, here's a couple of things to talk about. Okay, so we are given a vector valued function R of t. Okay, I would like to calculate a vector that's going to be tangent to R of t. So let's think about how we can do that. Okay, so one way that's obvious, if it's not obvious to you, then let me explain afterwards, okay? But for those to which it is obvious, then let me just say this. One way that is obvious to get a vector tangent to R of t is to calculate R prime of t. That's going to be tangent to R of t. Okay, now, for those of you to which that was not obvious, why is that? Because remember that the derivative in a real valued function, the derivative tells you the slope of a graph. And for vector valued functions, the derivative of a vector is a vector. It's not a number. Okay, for a real valued function, the derivative at a point is a number, and it tells you the slope of the graph at that point. For a vector valued function, the derivative of a vector will be a vector, not a number. Okay, so instead of being the slope, which tells you how fast the graph would be going up or down, instead it's a vector. The derivative of a vector is a vector. Okay, so instead of being the slope, it is an arrow that's pointing in the direction of the curve. Okay, so if we did this, let's just suppose here, for those 3 points, let's call them R of T1, R of T2, and R of T3. Let's say those are those three black points. I'm ignoring the points labeled A and B, okay, because they don't have tangent vectors emanating from them. We could calculate tangent vectors there, but the person who drew this picture just didn't do that. Okay, so now we could say this, that first red vector is R, whoops, let's make that not so thick of a pen. Okay, so that first one then we could say is R prime of T1. The second red vector I could say is R prime of T2. And the third red vector I could say is R prime of T3. Okay, now that would not be wrong. However, here's a problem that I can easily avoid, and you can't avoid every problem, but problems that are easily avoidable, then we do a little bit of extra step to avoid the problem. Okay, now here's the problem. The length of R prime can fluctuate. So what I'm saying is I have three tangent vectors in the picture. R prime of T1, R prime of T2, and R prime of T3. Okay? Like I said earlier, in order to keep things consistent, it would be nice for my tangent vectors to all have the same length. But R prime of T1, R prime of T2, and R prime of T3 might not have the same length. So what we do is we standardize the length. I rescale those vectors so that they will automatically come out to have a length of 1. Okay, and what I do, the way that I do that is this. Let's erase this black writing just so that we have some more room here. Okay, what I do is that first red vector, I calculate R prime of T1, and then I divide that by the number. Here, I'm going to have to move it a little bit to have enough room. I divide that by the number magnitude of R prime of T1. In other words, I multiply the vector by the reciprocal of its own magnitude. And then that vector will be guaranteed to have a length of 1. When you take any vector and divide it by its own magnitude, what do you get? You get a vector where the direction hasn't changed, but the length has been rescaled to be a length of 1. Okay? Then the second vector here, you see, would actually not be R prime of T2. It'll be R prime of T2 divided by the magnitude of R prime of T2. That way it's guaranteed to come out with a length of 1. And the third one will be R prime of T3 divided by the magnitude of R prime of T3. So, what's the big picture? The big picture is, if we have R prime of T, okay, and then what we do is we calculate R prime of T, and then divide that by its own magnitude. What we get is we get something called a unit tangent vector. Okay, and we will call that capital T of T. So this is important. That's unit tangent vectors. And what they do is they indicate the direction of travel at any point along the path. Okay? So, pretty straightforward concept. But we need to know more than just the direction of travel, although that does tend to be extremely important. There's something else that you have to understand. The curve might be twisting as well. Think of an airplane flying through the sky, and the path of the airplane is tracing out the blue curve, okay? So as the airplane's flying through the sky, this is the path that it's following, okay? Here's the same picture right here. As the airplane's flying through the sky, that's the path that it's following, and we have 3 red arrows pointing to us the direction that the plane is flying at 3 particular points, right? But what do you know about the way that planes turn? They don't just, how should I say this? If a plane's flying along and then it turns, let's say you have an airplane, okay? And it was going in this direction here, okay? But look, the airplane has turned, hasn't it? How do airplanes turn? They don't just rotate, keeping the wings flat, do they? They twist as they turn. I think you all know that. Even if you haven't flown yourself, you understand that that's the way planes turn, right? They lean from one side to the other. They always lean into the turn, don't they? And that gives you a twisting motion of the plane. So if you have an airplane flying along that blue curve and it's changing directions at different points, it's also twisting a little bit. And the tangent vector does not show that twisting. It just shows the change of direction. So what we do is we calculate a couple of other vectors as well. Okay, now, one of them is called the unit normal vector. Let's do this. Okay, I'm going to erase that writing that's there just because it's taking up so much space. I'm going to write those again. I'm going to write them, smaller. So that we have here T of T1 T of T2 and T of T3. That's 3 unit tangent vectors at 3 different points. Okay, so what we do is we add on to that another important vector. What color should I make this one? How about let's make these this blue color, okay? Now, this is going to be a vector that is perpendicular to the tangent. Of course, we don't use that word perpendicular, do we? We call it orthogonal. I know I kind of missed a little bit, but whoops. See, I messed up. Give me a second here. I need to try to attach that. To the point there, and I'm having difficulty doing that, so give me 1 second here. Let's just try it one more time. There, that's better. Okay, that's called a normal vector. The tangent vector points in the direction of travel. The normal vector points orthogonal to the direction of travel. Let's call that one capital N of T1. Okay, now I'm going to do my best to draw the normal vectors at the other two places as well. Okay, now I'm going to draw this. It's not going to look perpendicular though. Let's draw it like that. Okay, that would be N, the normal vector at T2. Now I know that doesn't look perpendicular, does it? So this looks perpendicular, no problem. But the next pair at T2, they don't look perpendicular. Well, you have to remember, we're in 3 dimensions here. Even though the original blue graph, this guy here, was just in 2 dimensions, there's only an x and a y axis being shown. Okay, but remember, there is a 3rd dimension that exists. And things that are orthogonal to each other, as they rotate, but we still have to draw that in 2 dimensions, then the angles look weird to us. So I'm going to draw here that box to indicate that those are actually orthogonal. But what has happened? The vectors capital T and capital N have not only has capital T changed directions, but it has also twisted. And that has caused capital N to swing around a little bit. Okay? And then let's draw the normal vector at the 3rd point. Here, you know, it might have twisted around even more, and now it might be pointing like this. Maybe even like that. Oops. Okay? This would be capital N at the point T3. Okay, now, how do we calculate capital N? That's the question. So capital N is called a normal vector, and again, so that things are consistent, we don't want the length of capital N to vary. So we scale it so that it always has length 1, and it's called the unit normal vector. And let me write that word down. Unit normal vector. It's always orthogonal to the tangent vector. Let's write that down. Okay, but how do you calculate it? That's what I need to show you. Okay, so we have the unit normal vector, but how do you calculate it? Okay, here is the answer. It is equal to capital T prime I have not mentioned this before, but I'm going to mention it right now, okay? If you have a vector valued function and the magnitude of the vector valued function never changes, then its derivative vector will automatically be orthogonal to it. Okay, now capital T is a vector valued function. And the length of capital T is always 1. It's called the unit tangent vector. Its length is always 1. because the length is always 1, then the length's never changing. The length of the original function might be changing. But the length of the unit tangent vector is always 1, which means it's never changing, which means the derivative of capital T will always be orthogonal to capital T. So when I put capital T prime right here, it is guaranteed that this vector will be orthogonal to the tangent vector. But it's not guaranteed to have a length of 1. Just because capital T has a length of 1 does not mean that capital T prime will have a length of 1. So in order to make the normal vector have length 1, we calculate capital T prime and then we divide by the magnitude of capital T prime. And then that guarantees the magnitude of capital N to always be 1. So we've got the unit tangent vector points in the direction of travel and is 1 unit long. Then you have the unit normal vector, which is orthogonal to the tangent vector and has magnitude 1. Okay? The tangent vector shows you the direction of travel. The normal vector helps you to see if there's any twisting going on. And many books throw in a third vector just for good measure. Okay, now this third vector, okay, in addition to the unit tangent vector and the unit normal vector, some books throw in a third vector, which is called binormal, and it is orthogonal to both the tangent and the normal vector. So let me see if I can draw in here. What that would look like. Let's make this picture a bit bigger here. Okay, there we go. So let's label that with a capital B. Some books might use a different letter for it, but I'm going to label it with a capital B because it's called the binormal vector. Okay, and let's draw another one for here. Okay, and draw one for here. And that now gives you another vector. These are all three orthogonal to each other. Okay? Now how do you calculate that new vector, the binormal vector? Here's what you do. It's actually pretty easy. It is simply the cross product of the tangent and normal vectors. The unit tangent vector crossed with the unit normal vector, and that gives you the unit binormal vector. And that is orthogonal to both the unit tangent vector and the unit normal vector. Now, something interesting, you don't have to worry about the length of that. The length of that will automatically come out to be 1. And I'll show you really quickly up here in the corner why. Because the length, okay, Okay, that's going to be the magnitude of B is going to be the magnitude of capital T cross capital N. But remember something about cross products. The magnitude of a cross product equals the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them. What is the angle between the unit tangent and the unit normal vector? Well, they're orthogonal to each other, so the angle between them is pi over 2. The unit tangent vector has a length of 1. The unit normal vector has a length of 1. And the sine of pi over 2 is 1. And so you automatically come out with a magnitude of 1. So that's kind of nice. You don't have to rescale the binormal vector to make it have a magnitude of 1. It will automatically have a magnitude of 1. That's kind of nice. And by adding that binormal vector onto there, it just helps to show you a little bit more clearly any twisting. Okay? So here's what I do. Here's what I imagine. Let me erase some of this stuff here. The picture's getting a little bit crowded. Let's first of all make it bigger. But let's also erase some of these vectors. Let's just look at the first set. Okay, now we're just going to look at these 3 vectors right there. And I'll even erase the parentheses. Let's just call them capital T, capital N, and capital B. Okay, so what I do is I imagine that as an airplane flying along the path. Okay, and you have here the unit tangent vector pointing along the fuselage of the plane. Okay, so that shows you the direction the plane is traveling. And then you have the unit normal vector, I imagine, as the tail fin, or whatever you call that. Oops, hang on a second. I forgot what you call that thing that stands up there at the back of the plane. And then the binormal vector, I imagine as one of these back wings here. Okay? Those are all orthogonal to each other. And so I imagine those 3 vectors as sort of an airplane flying along there. And the red part, which is the unit tangent vector, shows me the direction of travel. The blue and the purple vectors, which are the normal and binormal vectors, helps me see how the plane is twisting as it turns. Okay? So you should be able to calculate here, okay, given any vector valued function, you should be able to calculate these 3 vectors at any location. Okay? Now, one more thing. This is a new topic, okay? We want to talk about something called curvature, which is a number that you use to measure how tight turns are. Okay? So, for instance, look at this portion of the graph here where it's straight. Okay? There, you would say there's no curvature. Well, technically, there would be a curvature, but the curvature there would be 0. Okay, but I'm going to write the words no curvature instead of saying curvature of 0, because I don't want to use any numbers here, because I have not yet told you how to calculate the numbers. So I don't want to use numbers there. Okay, so that portion there of the graph, where it's straight, the curvature will be 0, and I'm just going to write no curvature. Okay, this portion of the graph, along here, there's a bend, isn't there? It's not a very tight bend. It's a relatively slow bend. Okay, so right there we would have the curvature would be some sort of a small number. I'm going to write small curvature. Okay. Now, this portion of the graph, there's a really tight bend, isn't there? So there would be big curvature. Well, let's write large instead of big. So I would like to have a number that I could calculate that would tell me how much the graph is curving. Okay, so you see what I'm saying is that we might have a curvature of like 0 here, and maybe a curvature of like 1/5 right there, and a curvature of 3 right there. You see, and so by looking at the relative sizes of those numbers, because there's a curvature of 0 right here, then I know that the graph is straight. Because there's a curvature of 1/5 here and a curvature of 3 there, and because 3 is a lot bigger than 1/5, then I know that the blue section has a lot tighter of a turn to it than the green section. Okay, and there's even a little bit more to it. They're also turned in different directions, aren't they? The green section is turning off to the left, but the blue section is turning off to the right, which means that those two curvatures will also have different sign. One of them will be negative and one will be positive. It doesn't matter which one is which right now, but let me get rid of that green color because it's changing the color. You see, because the green section has a curvature that's a small number, and the blue section has a curvature that's a lot larger number, and because one of those curvatures is negative and the other is positive, then here's what I can say. I can say that the blue portion of the graph is turned it's turning in the opposite direction than the green portion's turning, and the blue portion is also turning a lot sharper. Okay, that's the idea of curvature. So let me show you how you calculate that number. There's many different ways, and you are welcome to use whichever one is easiest for you. So first of all, for the name of curvature, we call it kappa. That's a Greek letter, the Greek version of the letter K. Okay, it looks kind of like that. Actually, let me draw a little bit better. There, that's better. That's what a kappa looks like. Okay, and I'm going to tell you 4 different ways to calculate kappa, and like I said, you're welcome to use whichever one is easier. Okay, so one way of calculating the curvature is to take the unit tangent vector, calculate its derivative, so you have capital T prime, calculate the magnitude of that, and then divide that by the magnitude of your original function prime. Okay? You agree that you're going to end up with a number, right? Not a vector. You're going to get a number. So that's one way to calculate curvature. Okay? This is if you're given a vector valued function, r of t, then you can calculate curvature like this. That'll tell you how tightly the graph turns. Bigger numbers means tighter turns. Smaller numbers means not as tight of turns. 0 means no turn at all. Okay? When the sign changes, it means the direction of the turn is changing from right to left or vice versa. Okay? Another way you can calculate curvature if you think this would be easier, is you calculate r prime of t, little r prime of t, cross product with little r double prime, and then calculate the magnitude of that vector, and then divide that by the magnitude of r prime cubed. So once again, if you're given a vector valued function, r prime of t, then you can calculate the curvature with this formula. Okay? Or with this one, whichever one you want. Now there's a third formula that you could use that you might like even better. And that is this. If you're given r of t, and let's suppose, for the sake of argument, that you are told that that equals, and let's just put here x of t comma y of t. Okay, then this will also give you the curvature. If you do x prime of t times y double prime of t minus x double prime of t y prime of t, and then you do absolute value of that. I say absolute value, not magnitude, because this would be a number, not a vector, right? And then you divide that by x prime of t squared plus y prime of t squared and then you raise that whole thing to the 3/2 power. It's not obvious, but what I'm saying is that that formula and this formula and this formula, they'll all give you the same answer. It's not obvious that they're all the same, but I'm just telling you that they are, okay? We're not going to go through the proof of that. So you could use any one of those three formulas to calculate curvature, whichever one is easier for you. Okay? And finally, a fourth option. In this fourth option, what if, instead of given a vector valued function, what if you were just given a good old-fashioned y equals f of x? So something that you would have seen in calculus 1 or 2. Could you have calculated this thing called curvature for those functions also? Yeah, you could have. We don't cover that in Calc 1 and 2, but we could. And in that case, the curvature is f double prime of x absolute value of divided by 1 plus f prime of x squared raised to the power 3/2. Okay, so for a vector valued function, you've got 3 different ways to calculate curvature. For an old-fashioned y equals f of x function, there is this way to calculate curvature. Okay, and that's all we're going to cover today, and this is going to be the end of our chapter on vector valued functions. Starting after this, we're going to do what's called multi-valued functions. Have a good day.